Good evening, everyone. I was expecting to see faces I haven't seen before, so I have put a few slides together to tell you about our lab, who I am, and why I think I'm qualified enough to speak at this colloquium, or at least I think I'm qualified. So I'll skip through them quickly, because most of you know me, most of you know our work, and if you have questions, I will be happy to answer, but we can focus on the research that I want to talk about. So I want to briefly introduce our group. The group started in actually just over 4 years ago, in April of 2014, as part of their HEC's effort to increase the presence of internationally renowned faculty here at HEC and to increase the scope and the breadth of the research that we do. Since then, the group has grown. I mean, we are doing lots of things together. It's a fun bunch, and I'm delighted to be a part of this group because I learn more from them than I think they will ever learn from me. Each one of them is unique, each one of them brings a unique perspective, and we do lots of things together. We study, we learn, we write papers, we go to conferences, we have fun. And I think that's what is very important in this work, because as academics, you know that you can take us away from work, but you can't take our work away from us. So we're always working. And this group is something that gives me a relief from the everyday routine of administration activities. Our founder is a legend. Those of you who know anything about networks have heard the name of Stan Wasserman. He has been with us for 4 years. As of now, he's resigning as the head of laboratory. I will talk about that in a minute. But originally, he is a person of high scientific achievements. The book on social network analysis is rightly considered to be the Bible of network analysis because it was the first book that systematically brought together the knowledge that you guys have about graph theory into the language that social scientists could understand. Now, we both, I mean, the computer sciences faculty and the social sciences faculty study networks, but from different perspectives. What you call graphs, we call networks. What you call vectors, we call directed links, directed ties. So we have language that is similar, and I will use some terms interchangeably. But Wasserman was actually the first one to introduce this to social sciences and actually popularize networks in social sciences disciplines to a very, very large extent. He is a creator. He has created many things. New departments of statistics. His original training at Harvard was in statistics. He has created several consulting centers, several educational programs. One of them just opened up at Faculty of Social Sciences last year. It's a program in applied statistics with network analysis under the general disciplines of applied mathematics and informatics. So, I mean, if you want to get schizophrenia about this program with this direction at the Faculty of Social Sciences, that works just fine. Now, he recently founded Network Science Journal. It's a mathematical journal. It's indexed now already in Web of Science. For now, of course, it's Q4, but it's quickly rising up the ranks because it's very high-quality reviewers, high-quality papers. I highly recommend that those of you who do network analysis, network research, publish in this journal now while it's Q4 and under the radar, because it will be very quickly, very highly indexed. He's a jack of all trades. He's actually an amazing person. He plays golf almost professionally. He actually had his own jazz radio show. So, I mean, I guess talented people are talented at everything. He also bikes professionally, and he's a certified diving instructor. So, not that just he dives, he's also a diving instructor. So, he's an amazing bunch of energy that he brings with him everywhere he goes. So when he first came to HEC, that was, he was tough, but he was amazing to work with. And we are very grateful to him for the 4 years he's been with us, because this lab would have been nowhere without him. We started small at the very beginning. The story of the lab creation is actually interesting, but that's not what this topic is about, so I won't go into the details. But when we started, we did not have a research group. Lots of times when new labs are created, they have existing research group. Our research group was Stan Wasserman, NJ, our manager, and myself. So that was the dream team with which we just started working. And we had a dream to make this lab the largest in Russia and world renowned, and we actually have accomplished this task. We are the largest applied network research lab. We have been that for the last 2 years here in Russia. Now, we have about 28 lab members, a lot of them very young. We have lots of kids, lots of students. They come and go. Unfortunately, in applied statistical laboratory, lots of students come to us, quickly gather their skills that are so needed in the outside world and leave before we can hook them into research, into science. And takes a lot of effort to train them, and then we lose them to Sberbank and Deloitte and Volkswagen and all of those groups that pay a lot more than we can, at least at the beginning, to young trainers. So opening a master's program was one effort to teach them quickly, because teaching them in the lab walls and then losing them to the outside world was too costly. We have several colleagues who are not academics. They actually joined us from the outside world. They work in different departments at the companies that do analytical work. So even though the lab is for the network research, because we do applied projects, we have to use a lot of other statistical tools, not just networks. So we focus on development, education, and promoting the HEC brand. I will not talk about this a whole lot, because hopefully you have heard about our best program in applied statistics with network analysis. It is the best in Russia because it's the only one, right? We do not compete with programs that are open to the Faculty of Computer Sciences. You do a great job with data science programs. We are different. I will talk a little bit about why we are different. But nowhere else in Russia they offer that applied focus to the programs, and actually applied programs are rare. There are only 12 of them in Europe. Ours is one of them. We've been to many places. We go as a lab to at least one conference a year. It's a great community building effort. We are grateful for the support we get from HEC for our academic mobility. And we've done a few things. Of course, at the Faculty of Computer Sciences, you guys publish a lot more than we do. So when I tell you we published 34 papers in 4 years, that's like, okay, big deal. We do that in 2 months. We publish with a different focus. Our papers take much longer to develop. We have a thing that's called theory. Okay, it's this scary word that means nothing to computer scientists, because your theory is the work you do. Our theory is the answer to a question, why? Why do social constructs relate to each other the way we do? And then we have to find an explanation. I mean, of course, nobody questions the theory of gravity, right? Even though it's just a theory, but nobody jumps out the window. Now, we question all the theories we have. The two major theories we work with are social selection and social influence. Try writing that up in 35-page papers. So for us, 34 papers is a lot, and a lot of them are written by younger members, younger faculty members. So it's a very young lab. We have excellent diploma defenses, we have best paper awards. So we've done well for as young and as little as we started, okay? We are known outside of the world, like I said, at the international conference, we're known much better than here in Russia, even though we started popularizing network methods with regular research seminars, trips, summer schools, and everywhere else outside of Moscow to specific universities. We've been to a few places like Novosibirsk, Tomsk, St. Petersburg. We are trying to tell people how wonderful it is to study networks. I'm delighted to introduce the new scientific advisor of our laboratory, Dr. Anyushka Ferligoy, who is a mathematician from Ljubljana that has dedicated her life to popularizing network sciences in social sciences. Her husband, Vlado Batageli, of course, is the world-renowned creator of the program PAYAC. Those of you who work with large networks know that it's the only non-commercial computer program that can take up to 10 billion nodes. So, I mean, maybe you're not very impressed with 10 billion nodes. Maybe you do more, I don't know. I've never seen a network that large. So for me, 10 billion nodes sounds like a lot. So this husband and wife team will be our new core team. Yesterday, we call her Nusha. She calls herself Nusha. We call her Nusha. It sounded funny at first, now we're used to it. So Nusha introduced herself as the new scientific supervisor, talked to all of our members, and is very determined to take our lab to the new heights. We've done a lot of methodological work. So our lab has several groups. So that's why I'm saying that I think I can actually maybe talk to you almost on the same level. We have a group of mathematicians that works on new methods of doing things with items that are called nodes and with items that are called edges. They're called something else, I think, vertices, and I don't know what they're called in the world, and vectors. We have some papers published, and then we do have applied work. Now, applied work is something else. Like I said, we are working with social sciences. We are trying to find answers to questions. So a lot of work that you do is exciting, because sometimes when I read your papers, I understand what you talk about. My training is in decision sciences. So I understand the mathematics behind it. And once you develop a new algorithm, that algorithm sounds good, right? But the way that your paper is written, that algorithm is completely Greek, or I don't know, maybe Latin, or some other dead language to social scientists. They cannot understand math. But that doesn't mean that they shouldn't use the tools that you guys develop. So what we're trying to do is we're trying to translate that mathematical language into applied language and publish methodological work in sociological journals to people who can use these tools and instruments to answer real-life problems. And the real-life problems that we research, and that's the bulk of our work. So we do some math, but not very much. It's actually the group that's directed by Wasserman. I forgot to mention that Wasserman is staying on board. He's just stepping down now. But that's the group that's led by Wasserman, and that's the paper I will talk to you, project I'll talk to you about today. But most of our focus is on the projects that we solve. For example, problems in organization. When people have conflicts between each other, they don't talk to each other very well, a large project suffers. Or, for example, a large corporation that's trying to establish itself here in Russia, International Corporation, and they have problems between subsidiaries and headquarters. And we need to understand how the communication networks work in that organization, how the information flows. So we're trying to find answers to questions that actually of interest to real world problems. So we have lots of applied settings, and that's pretty much the focus of our work. And like I said, we open new statistical program. I'm sure you're following these trends. I haven't lived in Russia for 16 years. In the old Soviet times, they didn't give that much as capital punishment, right? Capital punishment was like, what, 15 years? So I've served longer than that in the US. So when I came back, I had no idea how much analytics was missing from the Russian corporate sector. A lot of you have worked in the industry, and you understand that there is actually very little analytical work that's being done simply because people haven't been trained in applied statistics. In the Soviet Union, we had planned economy, we didn't have to worry about profits, and then we were busy trying to develop planned economy. Nobody was really focusing on the analysis. Now, when we have two otherwise identical units, let's say in the energy sector, where the industry is very homogeneous, where we don't really have a whole lot of going on, but they're just so different in terms of performance, we have no idea why. And there is not enough analytically trained people who can help us answer these questions. So that's why we opened this program. We don't call ourselves data scientists, because we're not data scientists, we're actually applied data scientists, applied statisticians. And we combine the best tools of yours with some of the classical tools of Tukey and crew to bring the best analytics into the real world. And all of our students, we have 22 of them, are now gainfully employed. Those who haven't been now are. Again, they have gotten jobs way before we were able to train them completely. All right, we continue to dream big. So we have grown from that small kitten to that big lion that we are today, well known, with lots of publications, with lots of ambition. And now with a larger focus on better papers, on high quality papers, and publishing in best international journals. So Wasserman has given us a great start, and we continue to dream big. And those of you who are mathematicians, I invite you to read our motto. No hint. Oh, come on, guys, out loud. Oh, there is no infinity. It's let it be.
Greater than average.
Be greater than average. There we go. Math is a universal language. So the motto of our program, and that's printed on our t-shirts. I should have actually worn a t-shirt to show you. They look really cool. Is be greater than average, written in the language of math. Okay. With that, I'm going to talk to you about one project that was completed in our lab. It's a project, guess what, on missing data. Now show me the Faculty of Computer Science that does not work on missing data in network data, right? Because it's on the forefront of network research right now, precisely because if in regular statistics we're missing, in a perfectly random sample, we're missing a unit or two, who cares? Okay, big deal. We can impute. We have lots of different imputation algorithms. And of course, those in social sciences who are lazy, they'll just do averages. Those who do more advanced stuff will do maximum likelihood imputation or multiple imputation methods. But we can find that missing data point, and if we don't, big deal. Okay? In networks, it's actually not a big deal. Here is a real-life project. I told you we complete real-life project. So this is a real-life project from a real-life company. Okay, the company is large. This is the human resource department, people who work in the human resource department. And we have 71 employees in that department. We have asked all of them to participate in the survey. 67 people did. Now, if it were a regular sample, we were just asking sociological questions. We would be delighted, right? Great. 67 out of 71, who cares what those 4 are missing? What I have drawn for you is the network that we have generated as a result. People were asked in a free-form format. We didn't ask them to look at the roster. We asked them to name people they work with. One department in one company. And we get 3 disconnected components. Now tell me how that's possible in one department that people do not interact with each other. It's a multiplex design. We have asked questions following Krackhard on 4 networks: friendship, advice, boss subordinate, and professional, strictly professional relations. So we have 3 disconnected components that somehow do not talk to each other. Is that possible, or are we missing a bridge somewhere? Okay. So the project that I'm talking about today is motivated by something we see all the time. If we do not have 100% coverage on the network that we are trying to survey, we are going to get meaningless pictures. I mean, I don't want to call this network meaningless. It has provided us with lots of answers. We have given the report to the company. We just don't know how these 3 large disconnected components should be connected together. We're missing either a secretary, those secretaries, the weak link people are the most important in the network. Or we're missing the bosses of some subunits that connect this whole thing together. We're missing someone. The problem is we do not know what those nodes are. We do not know their attributes. And if in computer science, and correct me if I'm wrong, but if in computer science you are concerned with nodes themselves, right, in the network, we are more concerned with attributes. Because attributes in a network sociological study explain much more in terms of the variance than any of the network structure. Individual attributes matter. There is only one of Steve Jobs. Yeah, Tim Cook is trying to emulate him. I don't know how good of a job he does. It's hard to tell, but he's still not Steve Jobs, not in my eyes. There is only one Mark Zuckerberg, right? Maybe nobody's trying to emulate him now, but individuals matter, attributes matter to us, social sciences. Those differences matter, and we have no idea which differences we're missing. So we face this all the time, and it's a problem we have to deal with. Regular sociological recommendations that says, well, you have to have 95% or more of the network coverage. They don't work because we're missing keynotes. Okay. So what the study is, the study goal was to investigate methodologically what is happening if we are missing certain types of nodes or certain types of edges in an actual applied setting. So I know you guys are working, I mean, I have my spies, but I know you're working on missing data projects and you're trying to estimate what happens when you're missing some nodes or the others, or when you remove some edges or when you remove some nodes, but you do it as computer sciences, right? What we're interested in the attributes, because attributes matter. So we are taking a network, we are measuring the individual attributes, and then we're trying to see what would happen if we didn't have the complete network. Would our results of an actual study, applied setting, would differ? Okay. So sampling that's random is not, of course, appropriate for us, right? We can't do random sampling. Because sampling randomly, we're missing a whole lot of network. Complete network approach is not feasible, not always. I mean, how do you, if we can't get 71 people out of 71 in a real life company, right? How are we gonna get hundreds? And of course, when we work with network data, we assume that no data is missing. Otherwise, we can't make any inferences. So there is a very good journal called Network Science, Social Networks, that has been around since 1979. We're approaching 40 years of social networks. It has been a bridge between different disciplines, including computer science, where people publish good work. We are working on a study now that looks at the co-evolution of the journal and the field of social networks, trying to figure out what influences what the most. Does the field influence the journal? Does the journal influence the field? So I'm very familiar with the studies that are published there. Guess what? I think out of applied, I probably wouldn't be mistaken if I would say that out of applied studies published, where people collected network data, 99% have incomplete networks. But we analyze them as complete. Okay? I think I've motivated this enough. Moving on. what we want to do is we want to look at the biases in the results that we get. We want to see if we have a cross-sectional study design, how do missing nodes and missing edges affect the study results? Same with longitudinal. If we have longitudinal design over time, we use Siena. I don't know what you guys use for working with longitudinal networks. We use Siena, and Siena has a 5% tolerance. So you can miss up to 5% of nodes between one study and the other, and Siena does okay. If you miss more than 5%, it just goes crazy and doesn't do anything, and you can't trust the results. Well, is that 5% an appropriate tolerance level, or do we need more than that? Or can we have more than that? Okay, so that was the question.
Sorry, what are the figures? What are the alters?
Of what?
Alters.
How does eliminating alters and their links applies?
Oh, sorry, that's our terminology, right? We have ego network design where the person we survey, we call him an ego. I mean, this is Freudian approach. I should have said that we have our own terminology. The connections that the ego names are called alters. Don't ask me why.
Connections?
Yeah, the ties, the people that he's connected to. So basically what we do in our network, maybe I should backtrack to the way we do things. We take people, we ask them, please name people who are your friends, and we provide what we mean by friendship, because different people.
That's actually same etymology as the Russian word "drug."
Exactly. Exactly. Or name people who you think
Another one.
You can ask for advice, right? So the people they name are called alters. So it's the ego-alter relationship. I don't know how this terminology has gotten into the network analysis in the social sciences. Okay? So it's just the person who we survey is ego, the people that he or she names on the survey are alters. Okay? I think one of the reasons why I'm doing this presentation in English is that because I have no idea how to say this in Russian. У меня нет перевода. Я потом по-английски рассказываю, я схитрила.
Нет, ну как альтер-эго.
Так и есть?
Так и есть.
О.
Нет, ну друг, друзья.
Они друзья, если у нас friendship network. If we have a non-friendship network, for example, strictly professional network, or if we have organizations, we can have an organizational setting where an entrepreneurship, small organization names other organizations that it works with. Those will still be alters, but you can't call them friends. Banks are not entrepreneurs' friends. Well, they're neighbors in the network format, but again, adjacent nodes, if you want to call them that way, okay? Even though they may be adjacent, I think adjacent is the more appropriate here. They may be more adjacent if we actually establish the links ourselves through closed triads. So, I mean, alters means the person actually named them. Anyway, I think that we've beaten this to death. All right, so we look at the sampling bias. So if we have a certain problem in the way we collect data, and we of course have always problems in the way that we collect data, how does that affect our results? In social sciences, we have two axioms that we know to be true but never really prove, is that there is no such thing as independent data, okay? And there is no such thing as error-free sampling. So there are always errors in the data, and the data is always dependent. It's never IID, even though statistics tells us that it is so. So we look at differences in snowball sampling, link tracing bias estimates. Again, those are methods of data collection that we use. For computer sciences, that's completely irrelevant. And then the most important questions that we're concerned with is how does the lost information with missing information and with bias, how does that lost information affect our outcomes? What do we get as a result? Can we trust the results that we get? Can we help the companies that we work with establish certain practices and procedures? Or can we give them answers as to why one project is successful and another one is not? Okay, so that's what we're trying to do. Or in a large sociological setting, can we really explain why Trump won the elections and not Hillary, right? Because sociologists have been beaten up quite a bit over their prediction of Hillary winning the elections. Every poll that sociologists held in the United States prior to the 2016 presidential election had pointed to Hillary as a winner with a very large margin. With the probability that Hillary was going to win, I think, averaged across the polls was close to 73%. That's a lot. I might be mistaken on the magnitude, but it's 73, 79 something, way over half. Okay? Sociologists missed the point. Why did they miss it? At the same time, network researchers did not. It was network analysts who predicted that Trump would win. Okay? So we have these real-life problems that we're trying to address and real-life questions that we're trying to answer. And when the data are missing, we are having problems. So we're trying to see where in this huge part that's called node attributes, the characteristics of individual nodes, that to you may not be of much concern because a node is a node. To us, is paramount because we can't analyze any of the problems we work with using this wonderful network methodology if we do not understand how attributes change and what determines which node is missing and how important is that node. Okay? So we have used things that you guys know well. We use the ergoms to estimate at first the study design. And I explain what ergom is because this presentation was created for somebody who's not a computer scientist. Okay? And then we look at sampling models and how they assume. And then, of course, we look at comparing the incomplete data with the complete network data to see what's going on. All right? Now, how did we do this? We have a complete group of 190 students. It's a full network design. We start with a full group, and we have several waves of data collection where we ask questions. Obviously, we ask students to name the networks. We look for friends, we look for people who they study with, and sometimes they are friends with people who they study with, and sometimes they're not, if the study group is put together by a professor, let's say. So when I teach my courses, and when I divide students in groups, I do not allow them to select their own group. I tell them, you're going to work with this, this, and this person, no questions asked, because when you're out in the real world, nobody's going to ask you who you want to work with. You just deal what you have to deal with, right? So when it's this design of a study group, you're going to have different intergroup dynamics than if students are allowed to pick their own study buddies, right? So these networks, friendship and study networks, are different by their content. So we have the same nodes but connected differently. That's the multiplex design. And we have several questions that we ask them. Some of them are actually, of course, they're students and they're adolescents. By the way, nobody is asking, you can stop me at any time and ask questions, but nobody has asked why you're using student data. Well, students are the easiest to collect data on. Students are also people, so they happen to have attitudes and behaviors and emotions, and we can actually force them to answer questions when they're in the classroom. They're the easiest to collect data from. In real life setting, it's much, much harder. But of course, we have bullying and sexual violence study, and we use that study as a setup for our study because they had excellent questions, well validated, meaning they perform well when tested over and over. They have excellent retest reliability. And we wanted to see how responses to these questions, the node attributes, and the network design change from time to time, and how missing nodes affect the real changes that go on. So we have a full network, and we collect data every time on this network. And then in the next phase of the study, I will talk about this in a minute, we start randomly removing either nodes or edges to see what happens with the outcome. So the key outcome variable is bullying. Bullying, we have all survived high school, right? And they hear this story is much harder for boys than it is for girls, even though girls can be tough also. But bullying is a problem. It's a problem in American schools, it's a problem in Russian schools. It's one of the biggest issues that sociologists study in adolescent studies. And we have lots of covariates. By covariates, we mean other variables that we measure, such as masculinity or femininity, right? Those are measures of how does a student appear? Do they fit the traditional gender roles that are prescribed by the society? And of course, boys that appear more feminine are often subject to more bullying. And lots of times, students of non-traditional orientations are subject to more bullying. So it's important to understand what are the differences that we see in the behavior, and especially in the manifestation that we see in those attributes. So as I'm talking about the study, I hope you realize that attributes are different. Our nodes, each node is unique. So when we're taking a certain node out of the network, we are changing the dynamics of the remaining relationships. We also have demographic information. That's just vanilla stuff. It's not that interesting. And then we run P-star and we run the Siena on this data. So we look.
What do you run and what does the state compute?
Okay. Exponential random graph models, other models.
And what's the goal?
The goal is to estimate the probability of a tie formation for a complete network. So we have this complete network of students, each with their own attributes, which we use as covariates, as node covariates. We have the complete network structure that has triads, that has dyads, that has clusters, that has cliques, has all of those characteristics that we can use to predict the probability of the next tie formation, right?
The next
Tie formation.
tie formation, so kind of clique you mean?
The clique is a complete.
What's a tie formation?
Exponential random graph models predicts the probability that the two nodes that were previously not connected will establish the connection in the next period. Okay, so by tie formation we mean creating a link where there wasn't one, creating an edge where there wasn't one. It's I guess I should have backtracked into what's called that scary theory part, right? The models of social selection, where we're trying to determine how do people form relationships. It's important, especially in, well, actually it's important for anyone. Who do I connect with? Myself as a researcher, who will I write my next paper with? Right now it's an important area of study in sociometrics when we look at people's co-author networks and how they're affected by, I don't know whatever attributes we measure, right? So who will I form the next tie with? Out of this group that is listening to me attentively right now, will there be anyone that would want to have a project with me, okay? We can estimate this using the exponential random graph model. We put this network, who have I known before I came to this room, a couple of new faces, one of them is recording this show, and then attributes, what are the topics you work on, gender, age, interests, time availability. We put all of this together in this model that looks like complete mystery, like, you know, this neural network to our sociology. And of course not mystery, it's Bayesian Monte Carlo Markov chain simulation that allows us to do all of that. But anyway, we put all of this in the model and it spits out the result that tells us, is our network random or does it actually look non-random? Because if our network is random, that you guys can generate from just a random matrix, it's not interesting. Usually,
You said the program tells you what will be new connections, but now the program tells you whether the graph is random or not.
The program tells me several different things. First of all, whether the network we are analyzing is different from a random network.
Yeah.
Okay? That's the very first and very important question that we look at, because if our network is formed randomly, and random networks are usually formed in children of younger ages. When you take kindergarten, put kids together, they will just happen to talk to whoever sits next to them. Okay, that's a random network. As we get older, our networks are becoming less and less random and more meaningful. So as sociologists, we're interested in the meaningful networks. So the first piece of information we get out of exponential random graph models is this network random? If it's random, we stop. There is nothing else to study. If it's not random, we look at, does it have more ties than a random network or fewer ties than a random network? So we compare everything to a random network, right? So if it has fewer ties, why do we have fewer ties? We should have more of them. In a sociological context, why is this network so sparse? This is one of the mechanisms that then later used in community detection when we're looking for terrorist networks. Terrorist networks are exceptionally sparse. Each person has one or two connections, maybe, right? And that's how in a large agglomerate of a social network, we can find some empty spaces and say, well, something is going on over there. At the same time, some communities are very tight. For example, religious communities. They're very, very well connected together. They have more ties than a regular person can hold. I mean, I'm sure if you think about it right now, think of yourself, how many people do you interact with meaningfully on a regular basis, and students don't count? Because students we teach to, right? We talk to them, that's our job. But in a social circle, once you are just a professional, a family man, a friend, how many people do you interact with? 5 to 7 tops. okay? This is the same reason why we can only remember 7 digits in a phone number and something else. We really can't hold more than 7 connections on average meaningfully. There are some exceptions to that. There are some people who are happy just being a part of a couple, and then there are those social butterflies that have 50,000 friends on Facebook, okay? But in between the two, there is the rest of us that form that 5 to 7 meaningful connections. So when we have more than that, what does that mean? That's another community, right? So that's the first piece of information we get. Is the network random? Does it have more ties or fewer ties than a random network? But once we have that, then we have the attributes, different variables that we put in the model, such as the network structure. In the existing network structure, is the network conducive to creating ties? Because if all we have is disconnected components, dyads or triads that are not connected together, then this network is not very good at combining itself into a more global agglomerate, okay? Do we have transitive triads? Do we have the forbidden triad, right? What Granovetter calls it. Do we have more connected components with some isolates? So the network structure itself might be more or less conducive to creating more relationships. So we look at how the parameters of the network can be used to predict the next tie formation. Well, you guys do that. I mean, because that's just computer science, right? That's mathematics. Once we have done a good job with mathematics, we're done with the structure of the network, we look at individual nodes. Because now node attributes, such as gender, such as the wealth that Florentine families, right? The classical network study. The wealth that they had. What's the reason why the Medici is the family that we know and the rest of them we haven't never heard about? I mean, of course, you've heard about this classical study, right? Then we look at other things like attitudes, behavior, manifestations of things that we're interested in, like bullying, right? Those are all variables that we as sociologists think we can measure. We think we can measure everything, right? We think we can measure love and hate and bullying. So we look at those attributes and we say, well, if this person, this particular person, is male of certain age and has 3 friends already and smokes and maybe goes out to party, how likely is this person to form that tie with somebody who is being bullied? Okay? If this one is a bully, what is the probability that they will become friends in this network? So we can evaluate this probability in general, or we can calculate for each individual node, of course, using the information we get from this random graph, exponential random graph model. So it's based on logistic regression, and we get log odds, and we have to take the inverse logit function to estimate the probabilities, but that's really the mathematics that I don't go into details at those talks, right? Because what we're interested in is really estimating the probability of a tie formation in the network in general or in certain parts of the network. Okay? And this probability of a tie formation, just take my word for it, is greatly affected by differences between the nodes, things that we call node attributes. Okay? Males, on average, are much less likely to form ties than females. So if we have girls in the network, they will form ties more and quicker than boys. And children of different grades, I mean, I'm sure I'm telling you things you already understand and know, but children of different grades are much more likely to form friendships inside their grade level than between different grade levels. And people of different races are much more likely to form ties within their own race than interracial relationships, okay? But that's just demographics. Think about if we start talking about things like attitudes towards politics. We had an excellent longitudinal study done in our lab where we looked at the coevolution of political attitudes and networks on our HEC students for 3 years. We have collected data on them for 3 years to see how the network of students who were put together in the first year of the studies here at the Faculty of Political Sciences, Department of Political Sciences, how the networks would change. That was the year 2014 of Krim Nashin sanctions and lots of political turmoil. How do these children who are politologists, political scientists, how do they form ties? And how do those ties change over time? Okay? The individual attributes were very important. How those children differed from each other, how those students differed from each other, was exceptionally important to that study. So that was a co-evolutionary study that was completed at our lab. It was actually very interesting, won a couple of best paper awards. Anyway, so we're using exponential random graph model, and we're also using Siena, which is the model that's longitudinal, that's looking at the tie formation over time, using the same basic principles of tie formation, okay? And then we started to play with this network. We had full network design, right? So we had all the students that we collected data on. And then we started to see how would our results that we obtained on the full network differ if we start just randomly removing parts of the network. If we emulate what happens in real world, when we just randomly miss some of the nodes or some of the edges. So we used some edge-generated algorithm that removed the edges and had the networks that were 90, 70, 50, and 30% complete. So in the first situations, we randomly removed 10% of the edges, leaving the network 90% complete. Okay? And then we looked at the missing nodes, where we moved the nodes and, of course, all the ties that the nodes have. And obviously, we would have much more ties missing when we do the node-based algorithm than the tie-based algorithm. That's why we have them at, again, 70, 90, 90, 70, 50, 30. And then we ran the models and compared them to each other to see what was going on, to see how our results would change. Any questions before I move on to results? Yeah, go ahead.
What do you modeling by removing edges? That's clear.
We are modeling the effects of missing data. So we have the models, right? We have models of social selection that I just talked about. What's the probability of a tie formation? We also have models of social influence. It has a big name. It's really nothing much more than regression, where we have...
These models are trained for the full network. So if you apply them on a sparse network, it's completely unpredictable what they will say, I guess.
Okay, I'm talking to a computer scientist. We don't train the models. In the world that we live in.
What do you mean with model?
What we mean by model is we throw the data in and we see what comes out, okay? So it's, if we talk about models of social influence, I think I'll start with that. We take dependent variable, that's bullying, okay? Bullying behavior, how likely is a person to be a bully? Bullying is a categorical dependent variable, so we use, of course, a multinomial logic model to predict the bullying behavior, okay? On a scale from 1 to 5. Independent variables are all demographics, some of the attitudes, and some of the network characteristics. We look at this outcome of bullying, right? So that's a regression, logistic regression model. Okay, we don't have to train it. We don't because it's based on data. It's not simulated. It's not random. Okay. For the exponential random graph model, when we form a tie formation, would the two people become friends? We use the network structure and the, again, node characteristics such as age, sex, whatever. We throw them in the model and we get the probability. It's a fixed number. It's not a random number. I mean, given these characteristics on the data, this is the result that we get on this particular sample in this particular setting.
Yeah, but you say logistic regression, so that means you still have a data set and
Correct.
A model that predicts, and this model that predicts is designed for a certain set of features. If you send, for example, network characteristics, how many friends a friend has, how many friends a person has.
As far as I understand, they take a whole network, they predict missing links, then they take a truncated network with 70% of the nodes or links, and again, for this particular network, they predict missing links, and then they compare the predictions from the first and from the second.
Correct.
Am I right?
So, see, the goal of this, the end result, is, I mean, I'm too lazy to flip to the first slide. Well, maybe I will flip to the first slide.
Yeah, but the first slide is some sentences.
Okay, to the first slide on the study, okay? 71 people in the company, in the one department of the company. We have collected data on 67. We have 3 disconnected components in the department that should be all connected together. We are trying to predict the effectiveness of this department based on individual attributes. We can't. We are missing important nodes. So if this were our simulated network, and there are several nodes here that connect our departments together, we can take this network structure, we can calculate structural holes, for example, or we can calculate some other network characteristics. Between the centrality is going to be huge, right, for those nodes. And that between the centrality is going to affect the outcome, and the outcome of the project, let's say financial data. So this is the real-life problem that we face when we collect data in a real-life setting. Some nodes are missing. But what we do not know is how bad it is when the nodes are missing. So how much of the information that these nodes take with them is going to affect the outcome? Would the outcome be vastly different? Will I get the same measure of performance on a full network as I would get on a missing network? Yes, I know they won't be the same. But is the difference statistically significant? And is it higher or lower? And what is the probability of both types of error? Am I overestimating or am I underestimating? Am I getting false positive or am I getting false negative results? That's what I have no idea when I design a study in a sociological setting. Okay? So the goal of this study overall was to take a real-life setting, real people, collect real data, estimate them, try to understand the relationships between them, see what those results are, take those parameter estimates, those regression coefficients, okay? And then randomly modify this network so our model is different and compare the results. See how much the missing information affects the results that, well, we hold true for this particular group because we know them to be true because we have 100% full network, okay? So we're trying to see, can we develop some generalizations from this study in order to be able to use them in future studies when we can come into an organization like that and say, well, yes, I have 3 disconnected components, but guess what? It's not a big deal. Because if I'm missing only 4 nodes out of 71, I can still generate meaningful results. Okay? Does that answer your question?
Yes.
Okay.
So it's a sort of cross-validation.
Correct. Correct.
But here with this picture, you cannot reconstruct that actually 71 are connected.
Mm-hmm.
Just the
Right.
no ties between components.
Right. Right.
So if you
I-
constrain to 67.
Yeah, I can't reconstruct the network. What I'm trying to understand is how important is it that I'm missing the 4 nodes? Is it paramount that I collect 100% of all the nodes in a sociological setting in order to be able to answer the question that I ask? Or can I just say, it's okay that they're missing? Big deal, okay? So I'm just trying to see if there is that applied implication for missing data. Okay? We've done some models with churn. We've done the same with study design and link tracing. I'm going to skip through some of those things of what we have calculated. And I won't talk about results because I think that's where it becomes really interesting. Because this is where we need your help because we're stuck on the next level, right? So we know that when maybe it was obvious to you before I started talking. It wasn't real obvious to me. When we started this study, we wanted to see how much missing nodes affect the results. And we know they affect a lot, even 10%. So we tried the 10% first because we know that most statistical software, such as Siena, has a 5% tolerance. So why even bother studying that? It's already been done. But even with 10% of missing nodes or edges, we run into problems, okay? What we do not know how to do next, and I think that's what the rest of the world is working on while we're trying to work on our sociological problems, is can we impute the missing nodes from existing networks? So if we know that the network is not complete, if we have 71 nodes and only 67 responded to the survey, can we, from the existing structure of the network, understand where the other 4 nodes should be placed? Okay? So, for our particular study, because we have measured so many attribute variables and so many structural variables, and we have done a lot of predictive work, we have realized that we have a lot of problems, right? Parameters have large standard deviation, even with 10% of the missing data. And as standard deviation increases, standard error also increases. And with increased standard error, we are running into false negative results a lot. So obviously, when some of the network is missing, what we are first and foremost unable to do is to create the models of social influence, what we call just regular regression models, when we're trying to predict bullying as the outcome. Not the network structure, but those behaviors that interest us. If we're interested in performance, organizational performance, or if we're interested in how much the boys at school would fight, apparently, even with 10% of the nodes, we are not going to find the relationships that are there, because that's the type 2 error in statistics or false negative result because of the inflated standard error, standard error of the parameters. Now, things get bad even for edges with nodes. We actually end up with both type 1 and type 2 error. So if we're missing edges, yeah, it's a problem. So we do not find the relationships that are there. But if the nodes are also missing, which is what is our case with this company we worked for, then we're also committing the false negative type error, where we find relationships that are actually not there. And that's something that we try not to do in social sciences, because of course, when applied to social science context, we are committing an innocent person to prison, right? We're using them. I use American justice system to teach type 1, type 2 errors. So type 1 error is when the person is innocent, but we send them to jail. Type 2 error is when the person is guilty, they really committed the crime, but we let them go free. So in the case of missing edges, we'll let the guilty person go free. Big deal, we'll catch him next time. But with missing nodes, we are actually committing to prison an innocent person. We are finding relationships that are simply not there. We are saying the organization is going to be more effective when it's not. We are saying that Hillary is going to win, when in fact Trump does. Okay? So in social sciences, these problems of missing data have a lot more meaning and a lot more effect than they could in computer science, when our neural prediction network just does not work very well. I'll show you some pictures, okay? And unfortunately, you cannot see very well, okay? So we are looking at all the variables that we have evaluated in the study. It's a lot.
So it's the node attributes.
Node attributes and structural parameters. Like up there, you can see three cycles, in degree, out degree, and then we have male, ultra male, ego. So we have both the structural parameters and the node attributes. We have their original estimate that we have generate from the complete network, and then we have deviation from the original estimates. And the further away is the bubble, the more we deviate with the true meaning of that variable. Okay? Unfortunately, you can't see very well. I can actually see it better on my computer, so I can help you with that a little bit more. But for example, here this, the perception of a person who is homosexual. Like I told you, it's a controversial study. Those are things that interest sociologists and adolescents. In period 1 and period 2, right? How do people perceive that person who has non-traditional sexual orientation? Or another one, bully behavior. How likely is this person to exhibit the bullying behavior? Will he be a bully or will he not be a bully? And apparently, some results deviate more than others. We divide them by groups, right? With small, average, highest deviance. The size of the bubble is actually the significance level, okay? And things get out of control real quick. So this is 10%, and already on the 10%, we are in the 2 standard deviations range.
I'm sorry, could you more clearly
Yes.
explain the whole picture?
Yes.
Like what is each bubble and the colors, etc.
All right. Okay. So here we have, we compare the results of the missing data with the originally estimated models.
And this is 90%.
Complete edges. Yeah, 10% of edges are missing. Okay. 0 means they do not deviate at all. Okay, the scale on the x-axis is the standard deviations. Okay, so we are starting with 2 because we believe in the Gaussian distribution, right? And we know that 95% of all data fits within the 2 standard deviations from the mean. Right? So that's our gold standard, right here. We do not want our data to deviate, our results to deviate more than 2 standard deviations from the mean, right? Because then we get into that very different tail of the distribution, right? And if whatever we have fits on this approximate 0, then the missing edges have no effect. Once we go outside the 2 standard deviations, we get significant result, which says they are significantly different from the originally obtained. Okay? So the size of the bubble means the significance level. And obviously, when the difference is significant, I mean, the larger the bubble, the more significant is the difference. So if we look right now over here, this particular attribute, and this is perception of a homosexual person in period 2, it does not deviate much from the mean, so it's not, it's within 2 standard deviations, but this deviation is statistically significant. So when we find the difference is small. It's within 2 standard deviations, but it's small but significant. Now over here we have some differences that are far away, and this variable is bullying behavior, right? We find some differences in behavior that are 2 standard deviations away from the mean. So we find the differences in the estimates, but they're not statistically significant. So yes, we get different behavior, but we can't say that it's statistically significantly different. Okay? So the level of significance, the p-value, is the size of the bubble. What we don't want to see is large bubbles far away. Okay? So over here we have statistically significant 0. There is no difference with the original estimate. Okay? So we want to see large bubbles, but in the middle. That's good result. Anything that goes outside is bad. So with 10% of the missing edges, on some of the, you can see that the network actually doesn't change much, right? Well, 10% of the missing edges, you understand the effect that that would have on their network itself. Not a big deal. Some things like out degree density, well, big deal, right? Reciprocity, I think, is approximately the same. Things like 3 cycles, they don't change much. So network structure, those green bubbles, doesn't change very much. Now, second group is the demographic variables. Okay? Is the person that we are dealing with a male or female? Do they belong to a certain group or do they not? The third group is the one that we're interested in as sociologists. Demographics we can do nothing about. If a person is male, the person is male, right? Of course, there are some extreme measures such as surgery, but we're not going to go there. All right, but the third group is what we are really interested in. We're interested in predicting behavior. This is what we are after as social sciences. This is our focus. We want to be able to tell if this particular person sitting on that desk is going to be a bully. And it turns out that even with 10% of the missing edges, we're in trouble. We are okay on network structure. We are halfway okay on demographics. We are not okay on the behaviors. Just with 10% of the missing edges, we see significant differences in what the result should be, the model that it should be, and the model that we get as a result of the missing data. Okay? Just 10%. Things quickly get out of control with 50%. And of course, with 70%, well, even on 50%, there is nothing we can do. It's gone, right? The models are completely out of control. So if we have, what does this tell us? If we have a network in an organization of about 1,000 people, and we survey 500, it's meaningless. For regular sociological study, 500 people in an organization is huge success. It's wonderful. We ask them questions, they tell us how much they like the school cafeteria, we're happy with that. If it's a network study, it's meaningless. Okay? With nodes, things are actually much worse. Much, much, much worse. Let me flip to the 10% here. If you see this 10% missing edges, the bubbles are much tighter around the 0. Okay? So yes, we're in trouble, but not as much trouble as we have 10% of the missing nodes. When we have 10% of people missing with all of their ties, of course, our networks notice that our networks don't really change much. Demographics is okay, but the attitudinal variables, the behavior we're interested in measuring, is, well, again, meaningless. Most important variables that we're looking at are not only statistically significant, significantly different, but on a very high level difference. Okay? So when I have my network of 71 people, and 5% of them, 4 out of 71, are missing, I already realize the impact it's going to have on my study. I might be able to somewhat reconstruct the network structure. I might be able to even guess their gender. I mean, knowing the genders of the group that's there, this is, you know, human resource department, I am willing to bet this presentation is going to be female, okay? But I cannot guess their behaviors at all. So this is what, yeah?
Have you tried to analyze whether these deviants depend from the such kind of things like, for instance, bully behavior is not so often as non-bully behavior, and that's why this kind of deviation is obvious.
Excellent question.
Because for some behavior features, you do not have this deviation.
Correct. Excellent observation. Now, I mean, I wasn't sure how much you're interested in that. Of course, there is a very large difference in the attitudes that we measure. There are certain attitudes that we call socially desirable. There is a social desirability bias. People ask me questions, are you a bully? Am I going to admit that I'm a bully? Most likely not, okay? Or if the people ask me, and you know, this is a society that's trying to raise tolerance, are you homophobic? Am I going to admit to it? Well, maybe in Russia I am, but in the United States, where the data were collected, I'm not, okay? So there is a lot of bias in the data collection. Some of the responses, of course, are less sensitive to social desirability bias or less sensitive to some of the less desirable behaviors. But in social science, we are interested in all kinds of behaviors. So, you know, we want to know how it affects different variables. We looked across and we looked between. So obviously over here, when we are dead center, right? And that's acceptance of the bullying behavior, right? It's dead center. So basically, when people ask, when we ask a question, do you accept somebody's behavior as bullying? They said no, universally. So once we have the missing data, it's still going to say no, universally, because it's affected by social desirability. Okay? So we have some meaning between the variables, and we can look into in detail into what are those variables that generate such variance, of course.
Well, I meant that from statistical point of view, if your feature kind of rare, then this is not a surprising feature.
Well, the question is
all these problems with enough power and so on.
The question that we asked did not look to identify whether a person is a bully or whether a person is performing a bullying behavior. We were identifying attitudes. What's an attitude of a person towards a certain behavior? So whether or not we have a bully, whether or not we have somebody who is subject to bullying, is irrelevant because we're asking a question, do you like ice cream? Let's put it this way, okay? So we're asking a question of how do you feel about this behavior? Or what do you think is appropriate? So people have opinions. So we're not looking for a needle in a haystack. We're not looking to identify a characteristic. Is this person a bully? We're not looking to identify a characteristic of a node. We're looking to evaluate the changes in the overall attitudes that we're getting in a group. Not the behavior, but the attitude.
Well, maybe it's a bad example with behavior, but what I see here that maybe if the number of the students in the complete network was larger, then maybe you would not get this kind of deviation.
Good point. What's unfortunate in this sense is that even 190 people in a network, for our
No,
setting
I
is
see
a lot.
problem. I mean that when you try to make these results kind of common for all networks, it's not true.
I think another axiom of sociological studies is that network studies are not generalizable. We're not trying to generalize network studies. And in fact, if you look at most published studies, social studies, it's very rare that we have a network that's larger than 100 people or 200 people. So most networks that we work with in real life settings are small, unfortunately. I've seen some studies where they would have 2,500 students, for example. I think Daniel Alexandrov here in St. Petersburg at HSC does some studies where he en masse asks students questions, and he has like 500 or 600. But those designs are extremely rare. What we deal with is smaller samples, in real life, smaller samples. And of course, we have chosen 190 because that's kind of in between the very big ones and the very small ones. When I showed you the network 71 people, that's typical. We have another project that we're working on. It's a smaller company here in Russia, 51 employees. We are looking at another organization. That one is large by our standards. It's a company that has over 20,000 people. 273 employees responded to our survey. We are ecstatic about the response rate because it's very difficult to get people to respond. So 273 is a lot for us. It's considered a large network in our life. It's not that far away from 190. So yes, statistical power is a problem, but statistical power is always a problem for us. In network setting, it's always a problem.
Might it be that locally the network is always very different? Inside the big network, you can look at components, and all these components are very different.
Correct.
So having more components and a bigger network will not help to make some inference.
Well, if we are looking at the local effects on the global outcomes, then I'm with you. I think you're right. But in smaller networks, when we use ERGM exponential random graph models, we can account for those differences. We can take the connected components and use them as the covariates in the model. In a very large network, I think it's going to be somewhat meaningless because when we have 300-400 nodes, how many of these people are really connected together, and how do the local processes really affect the global outcomes? I'm not sure that would be of much interest to us. In a large school in America, maybe, even at HSC, I teach large courses. This semester, I taught 122 little sociologists, 5 groups. They're so different between each other. So, I mean, I can't even use those 122 as one network. I have to use 5 little networks of 25 because the dynamics within a classroom, as you know this very well, vary widely from one class to the next. So the global network of 122 students of one class of sociologists is not nearly as meaningful as the locally connected components. So with 10% picture looks bad, it looks much worse. We can't tell anything even with, so I mean, it makes no sense to go beyond 10% because at this point everything is out of control. So from the applied standpoint, the results that we will get are going to be meaningless. Okay, we're not going to generate anything. I'm not even talking about generalizability, but for that network, for that organization, we can't generate results that have the meaning when their missing study design is so different from the full network design. Okay.
What are the very first 2 rows?
The first 2 words, those are constrained. So when we have, when we have constant, those are constants. Whether or not we had somebody who was always a friend of a person. Does a person always have one person who was always connected in every period? Constant friend. So because when we are missing, okay, think about it.
It deviates on all pictures.
It deviates widely. The reason why is I don't know about you guys, but when we were in high school, we had one best friend. We had a buddy that we always did everything together, right? Okay.
That's a female thing.
All right. We girls always have that one girl that we share all secrets with, right? The boy we fall in love with and the teacher we hate.
Not true.
Okay? Well, me, all right?
That's why they made so much.
And that's why they eat so much. We can't even agree within this group. But anyway, so somebody who they name a best friend, okay? One person that they name a best friend. If that best friend is missing, the whole picture is screwed up, okay? So where are we with this? Well, I don't know. So we have this largest network in Russia. We have this best program in applied statistics because it's the only one. And we are trying to draw inferences from the results that we get, understanding that if we have missing data, we have missing meaning, okay? So at this point, we do not have enough mathematical power or the computing power or mathematicians on board to try to figure out whether we can impute the missing node attributes. We are leaving this to you guys to help us out because I know you're working on that and you do much better job than we can, but we're looking forward to you completing those projects that you're working on missing data so that we can take whatever software you guys write for us and use it in our sociological studies, okay? Other questions? I have 4 more minutes and I'll be happy to answer anything else that's left.